The second half of Unit 6 is going to focus on electrochemistry, and that largely centers around redox reactions. And we did redox reactions way back in Unit 1, where we talked about the gain and loss of electrons. And so our little mnemonic was Leo the lion says grr, or we could use oil rig. And so losing electrons is oxidation, gaining electrons is reduction, or oxidation is loss of electrons, and reduction is gain of electrons. And so hopefully you remember that we did the half reaction method for balancing equations, and we talked about the fact that single displacement reactions, a reaction that you saw several times in first year chemistry, even though we call it a single displacement reaction, is really a redox reaction because it involves the transfer of electrons. And so if we think about, taking that copper, we coiled it around our pen or pencil, and then we put it into a beaker, and the beaker was filled with silver nitrate. And so what we saw over time was that this clear solution, or it was kind of a cloudy gray solution of silver nitrate, over time changed to blue, and it looked like there was fuzz, or in first year chemistry you may have called it mold, growing onto the copper wire. And of course, nothing was growing, but it was the silver that was falling out of solution as a solid, and the copper was actually going into solution as an ion. So if we think about those two half reactions, we had copper solid was forming Cu+, and of course to balance that we would need an electron. So this isn't a balanced chemical reaction, it's a half reaction, and we know it takes two half reactions to make a redox reaction. And so the silver was in solution, so we know that that was in its plus form. It actually gained an electron and plated out the solid silver. So that's what we saw. So what we can do is we can actually blow this up and treat it like an electrochemical cell. So we're going to just sketch a cell. So it's going to consist of two containers, and those can be beakers if you want to make big cells. They can be little spot plates if you're going to make a small cell. And we need some way to connect these two. So sometimes they'll talk about a porous disc, or you can even use something as simple as filter paper that's draped between the two. And we'll talk about what the purpose of that is. And so we're going to draw on our two electrodes, and on this side it's going to be our copper electrode, and on the right hand side we're going to draw in our silver electrode. Alright, and to connect the electrode together we're going to put in a wire, and so we're going to clamp the wire onto this electrode. Alright, so we know that this reaction happens spontaneously, and so we'll kind of connect this to delta G as we go. But that's the basic outline of our cell. Alright, so the liquid that's going to be in here, in this side, let's say we use just copper nitrate, and this side we'll use silver nitrate. And then on our salt bridge, let's use something that won't interfere. So normally sodium chloride is a typical thing that you can use on the salt bridge, but if we mix a chloride with the silver, we're going to precipitate out silver chloride. So we want to use something that's not going to form a solid with either of those. So let's go with aqueous potassium nitrate. So that's kind of the setup of our cell. And if we go back to our little half reaction so you can tell what's happening in the cell, we know that copper is giving up an electron. So it's losing the electron. So we would say that the copper is being oxidized, and then the silver is gaining an electron and forming solid silver. So since it's gaining an electron, it's being reduced. Remember, you can also look at the charge. It was +1 as a charge, and it's going to 0. So its charge was being reduced. So if we think about that, then we can think of, well, where is the source of electrons? We know they have to occur in pairs. If copper is giving up the electron and silver is sitting there and receiving it, hopefully it makes sense to you that the electrons are flowing from the left side cell to the right side. So we draw the direction of electron flow. So electrons are going this way. And the one that's losing electrons is the one that's being oxidized. That's called our anode. And the one that's receiving electrons is called our cathode. So one way to remember it is alphabetically. So we know that A comes before C in the alphabet, and O comes before R, right? So if you can identify the thing that's being oxidized and the thing that's being reduced, then you know which way the electrons are going to flow. It's going to go from anode to cathode. I would say in textbooks, 90% of the time, they're going to put the anode on the left and the cathode on the right. So what College Board loves to do on the AP exam is to flip them, because they're really trying to find out, okay, did this student memorize that it always flows from the left-hand beaker to the right-hand beaker? So if this cell on the right had our copper in it, then electrons would be flowing from right to left. So always identify, go back to your half reaction, see who's losing, who's gaining, label them oxidation, and then think about who's the source of electrons. Okay, so over time, if we go back to that first year reaction, we know that the silver is the thing that's building up, because the silver was in solution and now it's forming a solid. So over time, what's going to happen is you're going to get silver precipitating out into this electrode. So this one builds up over time. You may have seen that in the reading. And the evidence of the blue solution, right, when this copper was going into solution, we know that the copper electrode is actually being eaten away. So over time, there's not going to be as much. Oops, I just made my whole electrode disappear. So it's going to be eaten away over time. So it corrodes. All right. So let's talk about the salt bridge. The purpose of the salt bridge is to keep the cell electrically neutral, because you can't build up a charge on either side, because if you do that, electrons will stop to flow. So we need to keep the cell neutral. All right, so we know that if we have this salt, really what's present is K plus and NO3 minus. So let's focus on this left-hand cell for a minute. The reaction is copper solid is forming copper plus. So basically what's happening on this side, since the electrons are leaving, right, so they're leaving this way, we're increasing the concentration of Cu plus in the beaker, because that solid goes into solution, right? So that's a net result of the plus charge going up. Well, if the plus charge is going up, then the cell isn't staying neutral. So the way we combat this is in the salt bridge, the NO3 minus in this case, or the anion, is going to flow that way. So the anion flows towards the anode. How do you think we can remember that? AA. So it matches, right? The anion flows towards the anode. All right, and of course I want you to be able to explain why that is, but that's a little way to remember it. All right, over here on this side, if we go back to our half reaction, we had Ag plus, and now it's forming Ag solid. So the net result here is that Ag plus is going down. So if Ag plus is dropping, then the positive charge is decreasing. And what do we need to do to balance it? Well, in the salt bridge, the K plus can flow into this side of the cell. So the cation flows towards the cathode. So again, C and C matches up. So the cation flows towards the cathode. So that's kind of a picture of what the cell is. And we'll answer a couple questions below. What was oxidized? We already answered that the copper was oxidized and the silver was reduced. And then it says, how can we harness the energy from this reaction? Now, don't get too excited. There's not a ton of energy that's going on in this reaction, but we'll actually calculate it and see. So we could put a voltmeter right here. So we could take a wire, connect it to a voltmeter, hook the other wire up, and we could actually measure what that potential is, or the EMF, or the electromotive force. And so we would need some sort of voltmeter attached to the wire. And it's enough to get, a tiny little light bulb or maybe an LED to light up, but it's not a whole lot of energy. So the cell that we just drew is called a galvanic cell, also known as a voltaic cell. and it's a spontaneous reaction, which we just saw in the last chapter, that delta G has to be less than 0. So that reaction is actually giving off energy, and so the chemical energy could be converted to electrical energy. And so we have our two parts. We've got our anode and our cathode, which we labeled. And what takes place at the anode is oxidation. So oxidation takes place at the anode, and reduction takes place at the cathode. The purpose of the salt bridge is to complete the circuit and to keep the cell neutral. And the direction of electron flow is always going to be from the anode to the cathode. So for the cell potential, that's the pull or the driving force behind the movement of electrons. And that's called the cell potential, sometimes called EMF, electromotive force. And so you can measure it in voltages, and you would use a voltmeter to do that. And so now we're going to get into a little bit of, well, what are those potentials? So you can actually see what the voltage for this particular cell that we just drew might be. So when you measure potential, it's all based on hydrogen as being defined as an E naught of 0, so an energy of 0. And they used to give you these big long reduction tables on the AP exam. They've kind of moved away from that, and now they just give you the relevant reduction reactions. Now, it's important to note that they will be given to you as reduction, and so if you need to flip them, then you've got to make the sign be the opposite. And so to get E naught for the whole cell, remember naught just means standard conditions, you add the reduction reaction plus the oxidation reaction. And to be galvanic, or to be considered voltaic or spontaneous, all those things go together. So voltaic, spontaneous, galvanic, E naught cell has to be a positive number. It's the only way for it to be spontaneous. So one thing that you do have to get away from is if you come through and multiply a reaction by a whole number, you do not multiply the E naught by that number. And that's a really hard habit to break, especially after, you know, doing delta H and multiplying through by a whole number. All right, so we're going to practice some. If you have the table in your book, or you have a printed table of your E naught values. And we'll do these two as practice, and then we'll follow up with a second screencast to finish this section. So if we look at our two half reactions, we have Mg forming Mg2+, and of course to balance that I need my 2 electrons on this side. If I go to my table and I look that up, this is losing electrons, right? So this is my oxidation reaction. So I'm not going to find that reaction in my table. What I will find is the flip of that. And so in the table, it's negative 2.37. Here, I want to make it a positive 2.37. Then I've got 2H plus forming H2. So 2H plus forming H2. And of course, to balance that, I need my 2 electrons on this side. So this one's gaining electrons. So this one is reduced. And of course, that's the reaction we just saw that the scale is based on. And that's equal to 0. So this is my E oxidized, this is my E reduced, and so to get E cell, I'm just going to add those two up. And that's math that I can do in my head. You get a positive 2.37 volts. Alright, for the second reaction, we've got Cu2 plus going to regular Cu, and we need 2 electrons on this side to make it match. And so this one's gaining electrons, so that's our reduction reaction. I go and look on my table, and I find that it's positive 0.34, and I leave it positive because I'm taking it as written from the table. The second half reaction is 2Ag solid forming 2Ag plus. So for this I need 2 electrons. I'm not going to find that, but I'm going to find coefficients of 1, and then it'll be flipped because this is an oxidation reaction, and you're looking at a table of reduction values. So I do not multiply it by 2, even though it's been multiplied by 2 here. So I just take that E, make it the opposite sign, and I get negative 0.8 volts. Alright, so here my E naught cell is equal to negative 0.46. Alright, So they're asking which ones are galvanic. Well, we know to be galvanic it has to be spontaneous, so this is the only one that is galvanic. This one is not.